go.
All right, so welcome back. We missed Monday and Wednesday, but hopefully for the greater good. And we're here Friday. And if you're in 222, you were here yesterday. So thank you for your patience through all of this. So we missed 2 days. We meet 3 days a week. So that's a little bit of a chunk of time, but it's not going to be a problem, right? There's all sorts of extra stuff that we cover in this course that's not strictly needed for where we're going, but that's relevant to the topic in general, and it won't be a problem to work around a couple of days that we've missed. So reminder, Monday is a holiday, so we won't meet on Monday, so our next meeting after today will be on Wednesday. Okay. I made a few adjustments on Canvas, nothing too significant, but I pushed your homework back for a week. So your homework is going to be due. I didn't do that, did I? Yeah, so your homework's going to be due on Wednesday, so it's a week from when it was originally due on the 15th. We're pretty much finishing up our current unit on logic today, and we'll start moving into set theory probably later on today. So you're more than prepared to do that homework, but I didn't want to make it due on Friday. So that's due on the 22nd, and then the following homework will be due the following Wednesday. So I'll post that probably over the weekend, and that'll be more homework related to what we've been doing, which is proofs and fallacies and propositional logic. So I'll post that up at some point, and then there'll just be one less homework assignment for the course. So that's one change. The other change, which is unrelated to the strike, is quiz 1. I pushed that back a week because I'm not going to be here possibly on the 24th. So a week from today, I may not be here. I will have to post and let you know. I'm planning to be here, but if I'm not, then I don't want to have to deal with the quiz. So I pushed the quiz back to the 31st. Everything else on here should be the same. All right, any new questions on the homework? And if you want to turn it in early, you're welcome to turn it in, and I'll get a head start on grading them. Yeah. Okay. All right, good to go. All right, so let's talk more about proofs and propositional logic and good stuff like that. So I think we did a proof of this statement that if n is squared, then if n is even, then n squared is even. Is that the proof we did last time? Okay. So let me just kind of quickly run through that again. So if n is even, then n squared is even. That's the thing we're trying to prove. So step 1, n is even. We don't know that n is even. It might not be. N might be 17. But we're assuming n is even because we're going to do the following. We're going to say, let's suppose n is even, blah, 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 blah. Therefore, n squared is even. If we can fill in those blah blahs with logically correct reasoning, then we'll have shown if n is even, then n squared is even. So the reason for this is simply that it's a hypothesis. And that's really the only time that we're going to write down something that we don't know is true. We're going to say, well, we're just assuming it's true. And everything that follows, we don't know if any of that is true either. We only know that if this is true, then these other things follow. But that's what we're trying to show. If this is true, then that is true also. Okay, so here we use the definition of even. So the definition of n is even would be there exists an integer k such that n equals 2 times k. And that's the definition of even. And then, since we're trying to make a statement about n squared, we're just going to write down the equivalent of what n squared is, which is 2 times k squared, which is 2 squared times k squared, which is 4 times k squared, which is 2 times 2k squared, and that's algebra. But what we've done is we've written n squared as 2 times something, and I'm going to be a little rigorous here and say 2k squared is an integer. Why? I'm just going to say properties of integers. We know from school other courses that if we have an integer and we square it and we multiply by 2, we still get an integer, a whole number, right? So we're referring to those past lessons to say 2k squared is an integer. And since we've written n squared as 2 times an integer, now we can say n squared is even. And that's the definition of even combined with statements 3 and 4. And that's what we were trying to show, is that n squared is even, so here we can say QED. This style of proof will work for a lot of things. Let me show you another one that's going to look almost exactly the same. So let's prove if n is even, 3 times n plus 6 is even. Well, step 1, n is even. Step 2, n equals 2 times k. K is an integer. I'm not going to fill in these reasons over here because they're exactly the same, but fill them in when you're doing this on a homework. 3, I'm going to say 3n plus 6 equals 3 times 2k plus 6 equals 6k plus 6 equals 2 times 3k plus 3. That's algebra. And then I'm just going to say 3n plus 6 is even. Why? Because 3n plus 6 has been shown to be 2 times something that's an integer. That's the definition of even. So I skipped the step where we explicitly said 3k plus 3 is an integer. And so assuming n is even, we've shown 3n plus 6 is even. Let's prove that if a and b are even, then a plus b is even. The sum of 2 even numbers is even. Well, step 1, a is even. Step 2, a equals 2 times k. K is an integer. Step 3, b is even. Step 4, you got to be really careful about, though. I do not want to write b equals 2 times k. If I write that, I am claiming that b is equal to a, and that's not a claim that we are allowed to make. It doesn't say anything about a and b being equal to each other. But if I write b equals 2 times k, since a is also 2 times k, b and a would have to have the same value. And that does not follow from anything that we've been told. But I could write b equals 2 times j, where j is an integer, right? But I'll put a comment on here. Don't claim b equals 2 times k. Otherwise, b would be equal to a. So if you have multiple numbers that are both even and you're trying to write them as 2 times an integer, you got to use a different variable. Okay, this is perfectly valid. B is 2 times some integer j, right? It might be totally different from k. Does that make sense? That's a picky little point, but it always costs you a point or two on a proof if you do that. So save the points. Okay, so what should we do in step 5? Yeah.
I'm sorry, so for 2 and 4, what is the reasoning? Like,
That's the definition of an even number.
okay, gotcha.
And I should be putting reasons in here. Hypothesis, definition of even. Hypothesis, definition of even. All right, so what's our likely, yeah?
So we could plug A and B into the equation and factor out the 2.
Yeah, we're trying to make some claim about A plus B. We're trying to show something about A plus B. Let's use all this stuff that we've done to rewrite A plus B as 2 times K plus 2 times J. And we've done this a few times now, so you should get excited when you see something like that and say, hey, I can pull out a 2. And I just wrote A plus B as 2 times an integer. And that's all I need to be able to say A plus B is even. And that's our QED. Got the idea? And this works for lots of stuff. And the sort of magic of it is the realization that, hey, once I've added these together, I can write it like this. I can pull out a 2. Once I've added A and B together, I can put them in this form. And hey, I can pull out a 2. Once I have n squared and I've got 4k squared, I can pull out a 2. That will pop up in a lot of different ways. So prove if W and T are odd, then W plus T is even. Because guess what? Adding 2 odd numbers together also gives you an even number. But we can prove it. So how do we do that? W is odd. That's a hypothesis. Do you remember the definition of an odd number?
You give us 1.
Yeah, W can be written as 2 times an integer plus 1, where k is an int. That's the definition of odd. Got to use our other hypothesis usually, so we'll say T is odd. That's a hypothesis. So T is equal to, and what should we write here? Yeah, let's use anything other than k, 2j plus 1. J is an integer. That's the definition of odd. And then we're making a statement about W plus T. Let's add them together and see what happens. W plus T equals 2k plus 1 plus 2j plus 1. And now we just do all the algebra we can think of. 2k plus 2j plus 2. And again, hey, look, guess what? We can factor out a 2. That's algebra. And since I have a longer statement here, I'm going to actually explicitly say k plus j plus 1 is an integer. And that's properties of integers. And so w plus t is 2 times an integer. Therefore, w plus t is even. That's the definition of even. And that's what we were trying to show. If this, then that. Okay so far? So let's do a fun little sidetrack for a moment, and then we'll go back to doing these kinds of proofs. But this business of properties of integers, k plus j plus 1 is an integer. How do we know that's true? How do we know that if you add 2 whole numbers, you get a whole number? First of all, is it true? Do we believe this? two whole numbers, add them together, you're going to get a whole number. I mean, I can't think of a possible way that could not happen, where you add 7 and 5 and you suddenly get something and a half, right? It's just not going to happen. Division, you can get fractions, but adding integer plus integer should give you an integer. But how do we know that's true? It's a relevant question, because every pair of integers I've ever added has given me an integer, and every pair of integers any of you have ever added has probably given you an integer. But does that prove that adding any two integers gives you an integer? That's not a formal proof. That's a demonstration of the plausibility of that. But maybe there's two weird integers that nobody has ever tried to add together, and when you add them together you get, you know, something point something. And we need some way to be able to definitively say that's never going to happen. Add two whole numbers, you get a whole number. And that's kind of a hard thing, because there's a lot of integers out there. There's integers none of us have ever thought of, right? Think of a new integer and just like add 17 to it, and that's probably a new integer you never thought of. So people have spent a lot of time trying to prove things like this, and it kind of depends where you start from. When we talk about integers, we usually make certain definitions of what it means to be an integer, and we might actually say that the definition includes closure, that if you add two integers, the thing you get is by definition an integer. But somewhere, someplace along the way, somebody's got to do this work. Now, we don't have to do it. We can just say properties of integers and we can go on with our proof. But somewhere somebody had to do this. And so this kind of brings us to this person in the picture over here, standing beside Einstein, Kurt Gödel. This is not on the test, by the way. This is just kind of free for Fridays, because it's Friday before a 3-day weekend. So a pair of mathematicians in the 20s or 30s, I think it was in the 20s, set out to address this question of how do we know these fundamental things like adding two integers gives you an integer, or adding x plus negative x gives you 0. We believe that, we use that all the time, but how do you prove it? And so a pair of mathematicians, Whitehead and Russell, set about trying to rigorously prove lots of things about arithmetic. And there's a 2-volume collection. Volume 1 is 719 pages of this kind of stuff. And this is a weird language that can be used to prove things about proofs and about reasoning and about arithmetic. And I don't know who reads this kind of stuff. I don't. This proposition is much more used than star 10.2. Okay, so here's 10.22. I don't even know what that means. And DEM, that's a demonstration. This is the proof of that proposition, 10.22. And this goes on and on and on and on and on for hundreds and hundreds and hundreds of pages. And their goal was to take these things that we know about arithmetic, but try to put them on a very formal setting and try to prove everything. So we didn't have to simply assume, yeah, I think if you add x and negative x, you're going to get 0, right? And there's a really good page. Up here, this is on page 379, a section called cardinal couples. Cardinal numbers are what's being studied here. And there's some theorems and some proofs, and then there's a footnote down here. From this proposition, it will follow when arithmetic addition has been defined that 1 plus 1 equals 2. So all of this is like preamble to eventually proving 1 plus 1 equals 2. And we're like almost 400 pages into this book. Okay, this is serious stuff. I mean, these people were like intense, right? So we don't have to worry about this level of detail, but somebody had to. Here's the funny, strange, not necessarily funny, ha-ha part. Kurt Gödel on the left there next to Einstein. I mentioned him in the beginning of the course. So he presented a little paper at a conference around 1930 where he basically proved that you can never rigorously prove everything about an arithmetic system. And if you try to do it and you actually succeed in proving every possible theorem that's true, you're going to introduce contradictions. You're going to create paradoxes. And if you weaken your system of axioms, your system of things that you take as just we're assuming these things are true, if you reduce those to the point where you don't have contradictions anymore, then you end up with things you cannot prove. Things that are neither true nor false. And we'll dabble in both of those ends in a few weeks. When we get into set theory, we'll start looking at contradictions, paradoxes, right? Things that can neither be true nor false. And we'll also talk about things that are neither true nor false, things that are called undecidable. And Gödel showed that there's no sweet spot between having paradoxes and having things you can't prove or disprove. There's no magic balance point in between where you've got just the right stuff so that there's no contradictions and everything is provable as true or false. There's always either one extreme or the other. And there's no way to sort of find that place in between. And that's disturbing but also satisfying in some ways. So we'll dig into that stuff when we're doing set theory later on today and mostly next week and the week after. So weird stuff coming down the road. That's just kind of a preview. All right, so back to the land where we can just say properties of integers and nobody's going to complain. So we can prove things like this. Let me show you a pretty simple statement that is a little hard to do with this kind of proof. We know that if we take an even number and we square it, we get another even number. 6 squared is 36, both even. 8 squared is 64, both even. Let me give you a slightly different theorem. If n squared is even, then n is even. This is saying something very different from what we showed the other day. We've shown that if you take an even number and square it, you're going to get an even number. This is saying if you take any number and square it, and that square is even, then your original number must have been even also. So this is the converse of what we just showed. Right? We showed if n is even, then n squared is even. Now we're trying to show the converse. The converse is not generally logically the same as the original statement. And let me give you a quick example of why converse doesn't work. If n is even, then 2 times n is even. Well, we can prove that pretty easily. If n is even, n is equal to 2 times k, so 2 times n will be 2 times 2 times k. That's 2 times an integer, that's going to be even. Pick your favorite even number, 20. 2 times n is 40, that's even. Okay, the converse says this. If 2n is even, then n is even. Is this proposition true or false? Why is it false? Because if n is 7, 2n is even, but n is not even. So this is false. Remember, to prove that a theorem is false, all you need is one counterexample. You don't have to formally prove anything. If you can find one instance where the statement is false, then it's not a theorem. Well, we can just pick n to be 7. 2n is even, but n is not even. So the converse is generally very different from the original proposition. So even though we've proven if n is even, n squared is even, proving this is a totally different matter. So here we can start with n squared is even. That's the hypothesis. And so we can say n squared equals 2 times k, where k is an integer. That's the definition of even. But it's not clear where to go from there. Because if n squared is 2k, we could say n equals the square root of 2 times the square root of k. And now we just firmly left the land of integers. Because we got square root 2 in there, and it's going to be really hard to come back and actually make a statement about n as the product of an irrational number and the square root of this unknown integer k. So this is a problem that the method of proof we've been using doesn't really seem to help. Nothing jumps out and says, oh, just do this, and then you can do the same thing you did the last 5 times. It's a little trickier here. This is a problem that actually works really well in a proof by contradiction. So a proof by contradiction, the idea is, instead of assuming the hypothesis and proving the conclusion, we're going to assume the negation of the conclusion and then prove a contradiction. So proof by contradiction. So we're trying to prove P implies Q. Assume the negation of Q and then prove that false is true. That's a contradiction. If by assuming the negation of Q we can prove that false is true, then this assumption must never be true. Right? We must conclude that Q, not Q, cannot ever be true. Which means not Q is false. So this means therefore the 3 dots. So therefore not Q is false. Therefore Q is true. And we're also going to assume P, of course, because that's the hypothesis. And that'll be our QED. So the general strategy for a proof by contradiction, if we're trying to prove P implies Q, we're going to assume the negation of Q, right, as well as assuming the hypothesis. And all we got to do is find a contradiction, prove that false is true. And then we can back up and we can say, well, therefore, you know, Q must have been true. And more formally, what are we doing? If we assume not Q, and we can show that that implies false, well, we know the contrapositive of a conditional statement is always true. So this would imply that the negation of false implies the negation of Q. And the negation of false is true, and the double negation of Q is Q. And so proving this simultaneously proves that if true is true, then Q is true. And we know that true is true, and so direct reasoning, we can conclude Q. So we can do it in a very sort of formal propositional logic kind of way, but mostly the way I think of it, right, to prove if P then Q, assume not Q, and then prove something absurd from that. And since you've reached an absurdity like false is true, then this assumption must have been wrong. And since not Q is wrong, Q must be true. And that's going to work really well for this proof. And it's going to take almost no work because of what we've already shown. All right. So let's prove if n squared is even, then n is even. Okay, well, I'm going to assume n squared is even. That's the hypothesis. And I'm going to assume n is odd. That's my assumption. That's the negation of the conclusion. Right? So technically I'm assuming not n is even, right, which means n is odd. All right, well, if n is odd, what can we say about n? Okay, we can write n as 2k plus 1, where k is an integer. That's the definition of odd. And we're just going to do the same program we've been doing in these other proofs. Let's write n squared. That's 2k plus 1 squared. Equals 4k squared plus 4k plus 1. And can we factor this in a useful way? Heck yeah. Pull out a 2. 2 times 2k squared plus 2k plus 1. So n squared equals 2 times an integer plus 1. Right, that's algebra. And so n squared is odd. That's the definition of odd. But we also know that n squared is even. Well, if n squared is odd, then n squared is not even. Right, and that's also property of even and odd. Something's either odd or even, right? So we've proven that not n squared is even, but we also know that n squared is even. And so at that point I'm just going to say contradiction. Okay, so I use this kind of sideways number sign to mean contradiction. And my contradiction is between step 1 and step 6, or generally just step 1 and 5 would be enough to say that's a contradiction. Therefore, this assumption must have been wrong, so n is even, and that's what we were asked to show.
So I think I'm getting lost. So the contradiction is part of 6, or is it the like reasoning?
Contradiction is what comes after 6.
Okay.
So it's the next step.
Oh, gotcha. And then the reasoning for 6 is therefore n is even?
Yeah, I ran out of space here. Let me be a little more careful here. Okay, so step 6, not n squared is even. And so then I would say contradiction between step 1 and step 6, because one of them says P and the other one says not P, right? And so I would say therefore n is even, and that's QED. I don't know what I put for a reason, maybe P and not P, where P is the proposition that n squared is even. So if we ignore all of the stuff below here and we just think about what we did, prove that if n squared is even, then n is even. All we did was we said, suppose n is odd, then n squared is odd. right? So really what we did was we proved if n is odd, then n squared is odd. So that's all we're proving in all of these steps. If you take an odd number, its square is odd. Therefore, if the square is even, n cannot be odd. Because if n's odd, the square is odd. If you tell me the square is even, n can't be odd, so it's got to be even. That's the whole essence of the proof. Yeah?
So what we did here was check if it works both ways.
So after this, what we've shown is that n squared is even if and only if n is even. So here, the statement and its converse are both true. Not generally the case, but in this case it is. And we can do one more, and the one more is even easier because we've done the heavy lifting already. Prove if n squared is odd, then n is odd. Well, we already proved earlier if n is even, then n squared is even. So if n squared is odd, n cannot be even. So n's got to be odd.
What is the difference between a hypothesis and
And an assumption?
Yeah.
Hypothesis, so we're trying to prove if P, then Q. P is called the hypothesis. Okay? Q is called the conclusion. So since we're assuming the hypothesis and then trying to go from there, right? If I write down the hypothesis, I'm just going to say that's because of the hypothesis. When I wrote down n is odd, let's say assumption, negation of the conclusion. Right, we haven't been told that n is odd, but to construct this proof, I'm going to say, let's see what happens if n is odd. It's kind of the same thing as a hypothesis or an assumption.
Okay.
Really what we're doing is we're stating the negation of the conclusion.
Okay.
All right, so if we've already proven that the square of an even is even, this falls out with like a one-line proof, basically. Right? If n squared is odd, n cannot be even, because if n's even, n squared would be even. Since n squared is not even, n cannot be even, so n must be odd. Right, so if we know n squared is odd and we assume n is even, then n squared is even, and we get an immediate contradiction. N squared is both even and odd. And so this assumption must have been erroneous. Bless you. Making some sense?
Does the pound sign just conclude that like this can't happen?
Yeah, that's. I don't think that's a universal symbol. It's just what I use for contradiction. You could write the word contradiction.
Okay.
But we basically proven something and the negation of something. So everything we write in a proof is true, right? So we could always write this, and the conjunction of those two true things must also be true. So we've just proven n squared is odd, and negation of n squared is odd. And we have a theorem which says P and not P is always false. So we can conclude false from everything we've done, so we've just proven false is true. So that's kind of the quintessential contradiction. But as soon as you write two things that contradict each other, you're just 2 steps away from saying false is true. So proof by contradiction is a powerful technique. And we'll come back to it again and again. So let's work over real numbers for a moment. Suppose n is equal to a times b. Okay, I claim if n is equal to their product, a times b, then a is less than or equal to the square root of n, or b is less than or equal to the square root of n. And we can think about this and try to come up with a direct proof, but as soon as you have square roots in there, there's weird stuff going on. And we're talking about reals. Reals are squirmy things anyway, with all kinds of strange properties. But an indirect proof works really well on this. So here's the hypothesis. Here's the conclusion. So if P, then Q. So to do an indirect proof, I'm going to do the following. N equals A times B, that's my hypothesis. 2, I'm going to assume the negation of this conclusion. I'm going to negate this proposition Q that A is less than or equal to the square root of n, or B is less than or equal to the square root of n. So that's the negation of the conclusion, or the assumption. Okay, how can I rewrite this thing to get rid of that negation symbol?
We just flip the inequality signs.
We can flip the inequality signs. We can change the or to an and. We can use De Morgan's theorem. Okay, this is how we go from an if statement to a while loop in programming. If we have something that we want the loop to happen while it's, if we want to exit a loop on a condition P, then we say while not P, right? So sometimes when we're writing loops, we're thinking about when do I want this loop to exit. But to write a while statement, we have to put it in the form of a not condition that we want to exit. So, and that's using De Morgan's theorem. So let's apply De Morgan's theorem. Negation of A or B is the negation of A and the negation of B. And I skipped some steps, right? I should have written not A less than or equal to n and not B less than or equal to square root n. And then I have to state that if it's not less than or equal to something, it's greater than something, and that's properties of reals. But everybody okay with this? Right? If A is not less than or equal to something, then it must be greater than that. And De Morgan says we change the or to an and. And this should make sense, right? Our conclusion is that at least one of these numbers is smaller than the square root. The negation of that is both numbers are bigger than the square root. That's really all De Morgan is saying. I'm going to do A or B. The negation is I'm not going to do A and I'm not going to do B. All right, well, if A is bigger than square root of n and B is bigger than square root of n, A times B is bigger than square root of n times square root of n, which is equal to n. And we got to be a little careful here because we're assuming A and B are not negative. But if A or B are negative, then this is automatically true. Right? Because square roots are never negative. So if you were doing this in a formal proof, you'd want to deal with the possibility that A could have been -2 and B could have been -2. But if those are the cases, then we don't have to do any work. So if I multiply A and B, I get something bigger than square root n times square root n, which is equal to n. Right? But we know that n equals A times B, which is greater than n, which means n is bigger than n, which means n is not equal to n. You can write this a million different ways, but you've got a contradiction, right? Really, as soon as you get up here. we've shown that n is bigger than itself, and that's absurd. So negating the conclusion must have been erroneous, and so the original conclusion must be true. Yeah?
How did we get n equals a times b?
That was the hypothesis. All right, want to see one more? I'll show you the coolest indirect proof. So we talked about irrational numbers, right? And imaginary numbers and things like that. So an irrational number is a number that can't be written as a fraction, right? And we talked about how the Greeks thought that. Have we talked about irrational numbers? Maybe we haven't.
Briefly.
I tell you about the Greeks and their cult?
No.
Ah, okay. Pythagorean, as in the theorem, he studied numbers, and he actually kind of worshipped numbers, and he actually had a cult of fellow people who believed that there were answers to great mysteries in the study of numbers, and in particular whole numbers. And they were convinced that if you studied whole numbers deeply enough, you could understand the entire universe. And it was a bona fide cult, you know, secret meetings and membership and stuff like that. What?
That's dope.
Yeah, totally. And so Pythagorean triples, you know, are these magic things where you can have a triangle like this, and it's a right angle here, and each side is a whole number of units, right? Bricks or cubits or whatever you decide to use. And you can do, you know, a 5 and a 12 and a 13, and those are whole numbers of sides. And this was something they really grooved on, you know. And so Pythagorean Theorem, right, tells us this squared plus this squared is equal to that squared. And part of the idea of that is you can look at that equation, you can figure out when you have three integers that satisfy this property of being able to fit it exactly on the sides of a right triangle. But then there's this. A triangle whose two sides are both just a single unit in length. Simplest possible right triangle you could imagine. And they wondered, well, what's the length of this side? Well, they knew it wasn't an integer, because it was bigger than 1 and it was smaller than 2. So it wasn't an integer, but certainly it must be a fraction of two integers. Well, it's a little smaller than a half, or 1 1/2, but it's bigger than 1 1/3. And they started, you know, thinking about what the fraction might be to describe this length. Well, in their studies, they made the horrifying discovery that there is no fraction that corresponds to this length. If you try to write a fraction m over n, where m and n are these beautiful integers, these whole numbers, no fraction of this type ever exactly describes the length of this triangle. Okay, so we would call this length square root of 2, 1 squared plus 1 squared. And this is what we call an irrational number. Square root of 2 can never be expressed as the ratio of two integers. You can get close. 141 over 100 is pretty close. But no matter how big your integers are, you can get closer and closer. You can never get exactly the square root of 2. And the worst part was they actually came up with a proof of this. And it's an indirect proof. And they are able to absolutely convince themselves there's no fraction of whole numbers that corresponds to that hypotenuse. And that's kind of a bummer if you think that whole numbers and fractions of whole numbers let you understand everything and it can't even describe the length of a simple triangle. So this was secret knowledge, right? They didn't want people to know about this, but one of the members of their society actually started talking to people outside about this. And word got back around to the people, and they took him out for a boat ride and pushed him off. He was this older man. He was like in his 80s, I think. Took him out on a boat and pushed him into the water. And he actually swam back to shore and survived. But it's like, this was serious stuff. All right, so how did they prove that square root of 2 is not rational? Turns out to be a really simple, but personally kind of uninspiring proof. I can do this proof, I can nod my head and say, yep, I guess it's true, but it doesn't really tell me why it's true. Okay, but it's still a pretty elegant solution. So let's prove square root of 2 is irrational. Meaning we cannot write it as the fraction of two integers, a over b. Okay, so assume square root of 2 equals a over b, where a and b are integers. Okay, that's the negation of our conclusion. And we're going to argue to a contradiction from here. And then we'll have to say, well, I guess square root of 2 could not be written as a over b, where a and b are integers. I'm going to put one other condition on here. A and b share no common factors. In other words, this fraction is in simplest form. If we end up with the fraction 14 over 10, we would want to change it to 7 over 5. And we know we can do that, right? If there's a common factor, we can divide a and b by that common factor, and we get smaller versions of those. And if those share a common factor, we can divide those. And if we keep doing this, eventually it will have to end. Because if we divide a times by anything, it's going to end up being not an integer. It's going to be smaller than 1. So we're going to assume that the square root of 2 can be written as the ratio of two integers that have no common factors. Okay, so they're in simplest terms. Well, if the square root of 2 is equal to a over b, we can square both sides and say 2 equals a squared over b squared. And most of the reasons for this are going to be just properties of numbers. Well, 2 is equal to a squared over b squared, so we can conclude a squared equals 2 times b squared. Just multiply both sides by b squared. Well, if a squared is 2 times b squared, what can we say about a squared? Along the lines of what we've been saying most of this afternoon. It's equal to twice times something. Say again? A squared is even, because b is an integer, so b squared is an integer. A squared is twice an integer. A squared is even. And what can we say about a?
A would be even.
A would be even also. Good, you answered it before I found the proof we did. So a is even. And the reason for that is CSE 215, January whatever today is, 17th. All right. So we've proven that a has got to be even. Well, if a is even, then we can write a equals 2 times k. And if a is equal to 2 times k, then a squared is equal to 4 times k squared. And since a squared is equal to 2 times b squared, 4 times k squared equals 2 times b squared. I'm just substituting in. And I can divide both sides by 2. 2 times k squared equals b squared. What does that tell us about b squared?
It's an even.
B squared is even. And if b squared is even, b is even. And we've just reached a contradiction. Because a and b are both even, we can divide them both by 2. And our assumption was that a and b were integers and they had no common factor. So we reached a contradiction. and therefore square root of 2 cannot be written as a over b. And so if you're like me, you immediately run off and try to prove that the square root of 3 is irrational using the same proof and the same approach and properties of being divisible by 3 and squares being divisible by 3, and you're welcome to do that because you have a 3-day weekend. But this is a pretty cool proof, right? And this was known to the Greeks, so 2,500 years ago or so. But it's an elegant result. All right, so I will let that percolate in your minds, or you can forget about it. And let's switch gears, okay? We're going to come back to propositional logic in a few weeks, and we're going to talk about mathematical induction. And that's going to be kind of the key of CSE 215. It's going to be the biggest part of this course that goes directly into what we're doing in CSE 222. When we start coding recursive algorithms, mainly for manipulating a data structure called trees. So we'll be coming back to this and building on it, and I'll post a homework over the weekend, a week from Wednesday, that'll do more questions in propositional logic. But let's switch gears for about a week, and let's talk about set theory. And set theory is really, it underpins everything else that we do in this course in some way. Everything we're doing can be built on top of sets. And set theory is one of these topics where, we learn set theory in school, and it seems pretty simple. Okay, a set is a collection of objects. So I can have a set consisting of an eraser and a whiteboard marker and a pen, right? And I can have another set consisting of a mouse. And I can say, let's take the union of those sets, and I get a new set consisting of an eraser, a whiteboard marker, a pen, and a mouse. Or I could have a set consisting of an eraser, a marker, and a pen, and another set consisting of a mouse and a pen, and I could say, what's the intersection of these two sets? So what's in common to both of these sets? Just a set consisting of a marker. So the kinds of things we do with sets are pretty rudimentary. We take unions where we put things together. We look at intersections where we try to find things that belong to both sets. We can look at the cardinality of a set. Well, if my set consists of a marker, an eraser, and a pen, the cardinality of the set is 3. Why? Because it's got 3 things in it. If I have a set consisting of those and the mouse, what's the cardinality of this set? It's 4, because there's 4 things in it. Not a terribly deep concept, right? Why do we even need a fancy word like cardinality for that? So set theory at some level is going to be very kind of intuitively obvious. And this means it's pretty easy to sort of tune out as we're talking about it. Okay, this was how I spent my whole undergraduate life, was tuning out of courses after the first few days because I'm like, well, I know all this stuff. But set theory is one of these areas where as we talk about it more and more, we're going to go off the rails at some point. And we're going to start getting into some weird areas. And it's the weird areas where things get really fun and interesting. And we're going to find ourselves in some non-obvious, non-intuitive territory. So you got to stick with me through the stuff that you've already seen and that we've already done, because I want to put everybody on equal footing with that, and I want to make sure we're clear on our terms and definitions. But we will get into some weird stuff. Okay, I guarantee that next week I will get you into some of the weird stuff, and it'll be cool. All right, so what is a set? Well, here's a naive definition. A set is an unordered collection of things. All right, that's not a very legally sounding definition. An unordered collection of things. What kinds of things? Well, for now I'm just going to say any things that you want. Whiteboard markers, mice, pens, letters, integers, whole numbers, irrational numbers, whatever. Okay? Take a collection of them, put them together, that's a set. Okay? It's important that it's unordered. So generally if I have a set consisting of a pen, a marker, and an eraser, there's no such thing as what's the first element in the set. Now I might list the elements in my set as a pen, an eraser, and a marker, but I could just as easily say the set consists of a marker, an eraser, and a pen, and that's exactly the same set. Okay, a set is defined by the elements contained in the set, not the order in which they appear. So it's an unordered collection of things. We could call them objects. The formal word would be members or elements. And I've laid the groundwork for a really bad paradox, which we'll do next week, which forced people to come up with a more formal definition of what a set is. All right, so we can use letters for sets. So we could say, let S be a set. So we can write the following: X with this curly E followed by the name of the set. This means X is a member of set S. So if my set is a pen, a marker, and a mouse would be a member of the set. An eraser would not be a member of the set. So we can write a line through that membership symbol, and this means X is not a member of set S. So some more meaningful examples of sets besides markers and pens. The set of all integers, the set of all even integers, the set of all odd integers, the set of prime numbers, numbers that are only divisible by themselves and 1. Integers greater than 100. Negative integers, positive integers. Integers that are the square of another integer. So each of these defines a different set. And sometimes we can say, the set of integers bigger than 100, and we all know what that means. So 101, 102, 103, and so on. Sometimes we could define a set by listing all the elements in it. So T is a set of 3 integers, 5, 17, and 3. Sometimes we can define a set as something like this. V is a set containing 101, comma 102, comma 103, comma 104, comma dot dot dot. So what is this set? Well, it's probably the set of integers bigger than 100. But this can be ambiguous. I might have meant all the integers bigger than 100 but less than 200. Well, that's not a very easy thing to see from that. Or I could say, P equals 3, 5, 7, dot, dot, dot. And you might look at that and think, oh, you mean all the odd numbers bigger than 1. Or you could look at that and think you mean, oh, all the odd prime numbers. Right? So that's ambiguous. But usually we can infer what's meant by something like this. And if you ever see this on a question, like on a test or something, you don't know what it means, ask, right? Because it's taking some liberties with this. So for example, we could say, you know, I equals ... comma 3 2 1 0 1 2 3 ... That probably means a set of all integers. Right? We probably assume that these are negatives. We would probably assume that this pattern goes on in both directions forever. Yeah.
If sets are unordered, is it important that you have like the I1, for example, going from negative to positive? Or?
Nope.
Okay.
I could have written this as and we could probably infer what we mean there, or I could have written it as 0, 1, minus 1, 2, minus 2, 3, minus 3, and we might have inferred that also. But the set of integers pops up so often we have a special symbol for it, and the special symbol is this funny z with an extra line going down the diagonal. So this means the set of all integers. And sometimes we write z plus, which is positive integers. So this one is absolutely standard. Z means a set of all integers. Sometimes you'll see z plus to mean positive integers. Sometimes you'll see z star to mean non-zero integers. But I don't think those are totally standard. The funny looking n with the double vertical bar on the left, this is the set of natural numbers. Which usually means positive integers and 0. So 0, 1, 2, 3, 4, 5. But some texts don't include 0. In some cases, this is just a set of positive integers. Our text, I believe, includes 0. I tend not to use this symbol. I'll just spell it out explicitly. But natural numbers, right, the numbers that you see in nature, so we don't have negative numbers usually popping up. 0, maybe. The R with a double vertical bar, this is the set of real numbers. The Q with the double bar on the left, this is the set of rational numbers. So fractions of integers. And there's an ordering here, right? Natural numbers is a set that's contained inside the set of all integers, but you have to throw in negatives to get from naturals to all integers. And then if you take integers and you start taking fractions of them, you get the set of rational numbers. But that doesn't get you things like the square root of 2, because the square root of 2 can't be written as a fraction of integers. So you have to add in more stuff, the so-called irrational numbers, and that gets you to the real numbers. And you can go bigger than that, because there's things like the square root of -1, and there's no real number whose square is -1. Because squares are always positive or 0. So we invent a new number, which we call I or J if we're an engineer, to mean the square root of -1. Well, if you add that new number to the reals, you get a bigger set, which is called the complex numbers. And that's written with a C with a double bar on the left. And for a lot of purposes, that's as far as we have to go. There's senses in which complex numbers are the biggest set you need. And that's a whole nother branch of mathematics. But the idea is, if we think about equations, think about equations equal to 0, where your equations are allowed to have whole numbers in them only, right? Positive, negative, you can have squares and stuff. If I write x minus 5 equals 0, what's the solution to that? X equals 5. If I write x plus 5 equals 0, what's the solution to that? Well, it's not a natural number, right? It's this weird thing called a negative number. So we need to expand our notion of natural numbers to be able to say what the solution to this equation is. So now we've got negative numbers as well as positive and 0. So we've got the integers. When I say something like 2x minus 1 equals 0, now I need to go beyond the integers, because there's no integer that you can multiply by 2, subtract 1, and you get 0. So I've got to introduce this idea of a fraction or a rational number. And so here the solution is x equals 1/2. So now we've moved into the rationals. And then if I write something like x squared minus 2 equals 0, I got to expand my notion again, because there's no rational number that will solve this equation. The solution is x equals the square root of 2, and that's not a fraction. So we got to move to the rationals. And then if I write an equation like this, x squared plus 1 equals 0, there's no real number that satisfies this. Because any square is going to be bigger than or equal to 0, so a square plus 1 is going to be bigger than or equal to 1. So I have to add more stuff to my set of what x can come from and go into the complexes. But it turns out that any equation I write, any polynomial equation, using any coefficients that could be positive integers, negative integers, rational, irrational, real, or complex, I'm guaranteed all my solutions are complex numbers or simpler. So our expansion to bigger and bigger universes of numbers ends with complexes. That's something called the fundamental theorem of algebra. Beautiful theorem. There's like hundreds of proofs of it. And again, for our purposes, we don't really deal with these. We'll talk about them to discuss interesting properties, but most of what we do is still going to be integers, maybe fractions. And that's pretty much it, but mostly integers. Okay, got a few minutes left. More ways to define sets. We can list the members of a set. We can describe a set in words. We can use this ... notation. We can use these special symbols like Z and Q. Other ways we can do is something called set builder notation. A set builder notation looks like this. The set of all x contained in the integers such that x is bigger than 10. So this is the set of all integers, or let's say all x contained in Z. So that's what x epsilon z means, such that, that's what the colon means, and sometimes you'll see a vertical bar instead of a colon, and then this is the condition, x is bigger than 10. So the set of all x in the set of integers such that x is bigger than 10. So this would be the set consisting of 11, 12, 13, 14, and so on.
What's it say after the
Contained in Z. Yeah. And this is a powerful notation. The set of all x such that 2x is an integer. Well, that's a way to describe the even numbers.
Is it acceptable?
No,
to use
that's
a-
not right.
Can we use a pipe for the whole?
Or you can use a pipe instead of a colon. So the set of all x such that x over 2 is an integer, that's a definition of the even numbers. Because 3 over 2 is not an integer, 4 over 2 is. So 4 belongs to this set, 3 doesn't.
Can you expand the latter half and have
This thing?
I mean, like where it has x is greater than 10.
Mm-hmm.
Can you add another specifying?
Yeah, x is greater than 10 and x is less than 20.
What ands would you use?
You could say and, or you could use a conjunction symbol if you want to be fancy. And a lot of this is not a rigorously defined language, so we can use some judgment in how we specify these things. All right, we got 5 minutes left, but I'm going to let you out early because sometimes this class ends at 1:50 anyway. And I want to get into something big next, so we'll leave it there. Have a good weekend. No class on Monday, so I will see you on Wednesday. Don't forget your homework is due on Wednesday. Have a good one. I'll see you next time.